Chapter 5. Making Colours. The Giant Cuttlefish. In the first chapter we met an animal hovering under a ledge in the ocean. As it hovered, it changed colours, second by second. An initial dark red unveiled patches of grey and silver veins. Blues and greens seeped back and forth on the arms. In this chapter we're back in the water with this animal and its ceaseless transformations. A giant cuttlefish looks like an octopus attached to a hovercraft. It has a back shaped a bit like a turtle shell, a prominent head, and 8 arms coming straight from the head. The arms are roughly like octopus arms, flexible and unjointed with suckers. When you're facing a cuttlefish, these arms can look like they're placed in a roughly horizontal array, but they're arranged around the mouth, and like an octopus's arms, they can be thought of as 8 huge and dexterous lips. Tucked away near the mouth are 2 longer feeding tentacles, which can be whipped out to seize prey. The mouth itself contains a hard beak. A cuttlefish body has no spine or real bones, but there is a stiff cuttle bone, which looks like the inside of a surfboard, inside the shield-like back. The shield is fringed by a skirt-like fin, a few inches wide on each side. A cuttlefish moves slowly by undulating these fins. When it wants to move quickly, it uses jet propulsion with a siphon underneath the body that can be pointed in any direction. Most cuttlefish are small, measured in inches, but a giant cuttlefish can grow to 3 feet long. This animal is 3 feet long with a skin that can appear just about any colour at all and can change in seconds, sometimes much faster than a second. Thin silver lines wander over its head as if the animal is visibly electrified. The electric lines make the cuttlefish look like a hovering spacecraft. But the disruption to one's impressions, to all attempts to make sense of the animal, is continual. As you watch, bright red trails lead from its eyes. A spaceship crying tears of blood. Cephalopods in general, not all but a great many, are skilled colour changers. In this prodigious group, giant cuttlefish are perhaps the pinnacle, or at least the most colourful. Some degree of colour change is not rare in nature. Many animals can modulate their surface colour to some extent. Chameleons are the familiar example. But cephalopods are faster and produce a wider range of colours. In the case of large cuttlefish, the entire body is a screen on which patterns are played. The patterns are not just a series of snapshots, but moving shapes like stripes and clouds. These seem to be immensely expressive animals, animals with a lot to say. If so, what is being said, and to whom? The giant cuttlefish is also remarkable in another way. How disarming it is to find friendliness in a large wild animal. I do not mean a mere toleration of a human's presence, but an active engagement, the animals making contact with a foreign being. This is not routine in giant cuttlefish, but not rare either. Quite often you encounter a friendly curiosity. The animal comes forward with its skin in a quiet resting pattern of colours and shapes. The cuttlefish will hover close by, apparently trying to work you out. These are little studied animals. They've not been kept in captivity very often. Alexandra Schnell, one of the few people to study them closely in the lab, says that they do show hints of the same complex responses to captivity seen in octopuses. They ambush visitors with well-aimed squirts of water from their jets. But giant cuttlefish seem even more enigmatic and otherworldly than their octopus relatives. They have big brains, both in absolute terms, sheer size, and as a proportion of body mass. As far as I know, they've not shown the most striking marks of intelligence seen in some octopuses, puzzle-solving, the use of tools, the exploration of objects. But they've not been studied nearly as much, and their lives would seem to make such behaviours less useful than they are for octopuses. These are not clambering explorers, but swimmers. While giant cuttlefish might not have the protean inventiveness of the octopus, they do have features that stay with you long after you've been around one in the sea. The friendly curiosity, at least in some cases, or a wary engagement as they hover toward you and away, and those unending, astounding colour changes. Making colours. The skin of a cephalopod is a layered screen controlled directly by the brain. Neurons reach from the brain through the body into the skin, where they control muscles. The muscles, in turn, control millions of pixel-like sacs of colour. A cuttlefish senses or decides something, and its colour changes in an instant. Here's how it works. The skin has an outer layer, a dermis, that acts as a covering. The next layer down contains the chromatophores, the most important of the colour control devices. A single chromatophore unit contains several different kinds of cells. One cell holds a sac of a coloured chemical. Around it are muscle cells, 1 or 2 dozen of them, which pull the sac into different shapes. Those muscles are controlled by the brain. They stretch the sac to make its colour visible, or relax it for the opposite effect. Each chromatophore contains just one colour. Different cephalopod species use different colours, and usually the animal has 3 kinds. In a giant cuttlefish, the chromatophores are red, yellow, and black-brown. Each is much less than a millimetre in diameter. This device explains how cephalopods produce some of their colours, but not all. A giant cuttlefish can make red or yellow by activating chromatophores of one colour alone, and it might make orange with a combination of the two. But this mechanism has no means to produce many other colours a cuttlefish might display. There's no way to produce blue, green, violet, or silver-white. Those colours are produced by mechanisms in the next layers of skin. Here we find several kinds of reflecting cells. These cells do not display fixed pigments as chromatophores do, but reflect back incoming light. This reflecting need not be a simple mirroring. In iridophores, light is bounced and filtered through tiny stacks of plates. These plates separate and direct the light's different wavelengths, shining back colours that can be different from those that came in. The results include the greens and blues that chromatophores cannot produce. These cells are not attached directly to the brain, but it seems that some of them are controlled more slowly by other chemical signals. Just below the iridophores, the leucophores are another kind of reflecting cell. They do not manipulate the light, but reflect it straight back. As a result, they often appear white, though they can reflect whatever colour is around. As the chromatophores sit in a higher layer than the reflecting cells, all the reflecting cells have their effects modulated by what the chromatophores are doing. When chromatophores expand, this affects the light that makes it down to the reflecting cells, and hence what is shone back. Imagine looking at a cuttlefish's skin from its side. In a cross-section, we would see a top layer, then a layer with millions of tiny coloured sacs, each being pulled constantly into shapes that expose or hide the pigments inside. This will be happening at a great rate through the activity of many muscles. Some light would pass through this layer and reach another layer where it would be reflected and filtered between stacks of mirrors. Those cells might be changing their shape more slowly as chemicals reach them from elsewhere. Further down, a layer of simpler, reflecting cells mirror back whatever light reaches them. Suppose a cuttlefish has about 10 million chromatophores. Then, very roughly, we can think of that layer of the animal's skin as a 10-megapixel screen. Roughly, I said. Both because the pixels seem not to be controlled entirely independently of each other, but in local clumps, and also because each chromatophore has just one colour. Some of the pixels are also on top of others, so the same patch of skin can produce many different colours. The layers below the chromatophores then add more complexity. The cephalopod's coloured layers are thin and fragile. Cuttlefish look very different when they've lost skin through age or damage. Then you see dull white patches. The magic skin is a thin sheet on top of a plain white body. On the animals I watch, Reds are in some sense the base colours, the most commonly seen. These reds range from maroon to fire engine. A common decoration on top of the red base is a white silver as it appears underwater. The whites form veins and dots, making little jagged flashes or a line of pearls. Other colours appear in patches: yellows, oranges, olive greens. They may hold static patterns, but their colours are rarely fixed for long. Their dynamic patterns are like movies played on the screen of the cuttlefish's skin. An example is the passing cloud display. Alternating waves of darker and lighter patches move consistently along the body from front to back or back to front. Once I watched a large cuttlefish from above and saw the left side of its body displaying a passing cloud to another cuttlefish under a rock, while the right side was still and camouflaged, pointing out to sea. Cuttlefish's colour changes often occur in combination with changes to the shape of their body and skin. Sometimes they swim around with dozens of papillae or folds of skin sticking straight out from their back. These look like tiny versions, an inch or so high, of the plates on the back of a stegosaurus. These papillae have nothing hard inside them and can be produced in a second. The eyes are the sites of finely detailed modifications in skin shape. Many cuttlefish produce thin wisps and folds of skin above each eye. These look like carefully sculpted eyebrow extensions. At rest, the 8 arms of a cuttlefish hang down in front and look fairly similar to one another. A cephalopod's arms have been assigned numbers from 1 to 4, left and right. Starting at the top, there are arms left 1 and right 1. From the front, these look like inner arms. Outside these are arms left 2 and right 2, then the 3rd pair, and finally the 4th. In giant cuttlefish, the 4th arms are larger in males than in females. When showing aggression, males will often flatten their 4th arms into shapes like broad blades. Another aggressive gesture is to hold the 2 first arms up like horns. Some cuttlefish make these horns elegantly wavy. Others shape their arms into fiddleheads, hooks, or clubs. In the most elaborate cases, cuttlefish will arrange layers of arms at 3 or 4 different levels. The first arms will be held high and straight, the second arms will be horn-like at a lower level, perhaps with curled ends, with the 3rd pair below, and finally the 4th arms, flattened and made as massive as possible. There are some fish whom, despite their harmlessness, giant cuttlefish seem to positively despise, and their approach is generally greeted with arms raised into horns and hooks. All these behaviours vary across individuals. I've sometimes been able to recognise an individual over many days, occasionally over a week. It's not easy to re-identify animals who can change their entire colour and shape at will, but sometimes a distinctive scar makes this possible. Eventually, I also learned to treat some white markings on the skirt-like fin, which seem to be permanent, as a kind of fingerprint. Different individuals respond differently to me, though they're of the same sex and size, and in the same place at the same time of year. The most welcome style of interaction is the curious friendliness I mentioned before. Some individuals tend to come forward in a resting pattern of colours and watch closely. The friendliest of them have reached an arm forward to touch me. This is quite rare. The cuttlefish hovers, moving slightly with his fins or invisible jet. As we hover, he maintains a specific distance, edging back when I edge forward, and sometimes forward when I edge back. But eventually he lets the distance narrow until our bodies are only a few feet away. I move a hand out close to his arms, but do not touch them. The cuttlefish reaches the tip of an arm or two out to touch mine. Nearly every time this has happened, it has happened only once. After a brief touch, the cuttlefish shifts back to maintaining a few feet of distance. He was interested enough to touch, but having touched once, he returns to where he was. One possible interpretation of this action is that the cuttlefish is seeing whether I might be good to eat. But a person is much larger than a cuttlefish, whose usual foods are crabs and fish caught whole. I don't think they're interested in me as lunch. Some individuals, friendly or not, have distinctive styles of colour change. I've occasionally encountered cuttlefish who seemed to produce colours the others had not quite thought of, or patterns with particular brilliance. The first of these I named Matisse. He was a friendly cuttlefish I visited for several days some years ago. All his colours had particular detail, but something else set him apart. He would be hovering without fuss in some mixture of reds and whites and would suddenly explode into bright yellow. This flood covered his entire body with no other marks visible and would be switched on in less than a second. One moment he'd be dark red with veins and stripes, and in less than a second he looked like a cuttlefish-shaped sun. The flare would then fade more slowly. Oranges would appear among the yellow and darken. Patterning would return. In 10 seconds or so he was dark red again. The change to yellow was not accompanied by raised arms or other displays. There was no other sign of fuss. I've seen overall yellow described as a sign of alarm in other cephalopods. I suppose it's possible that Matisse was alarmed, but why did everything else about him look so calm? Occasionally he produced yellow patterns in response to intrusive fish, but these were deeper yellows combined with arrangements of arms. The uniform blazes of canary yellow I saw appeared to be part of a different behaviour. He just seemed to have a liking for these chromatic explosions. In the years since, I've seen quite a few other cuttlefish who produced these yellow flares, though none who lit the water up quite like Matisse. Given what I said about the machinery of colour change, it's easy to work out how this is done. A giant cuttlefish has some yellow chromatophores, so the flares were almost certainly produced by expanding suddenly those chromatophores and scaling back everything else. Well after Matisse had come and gone, a cuttlefish arrived whose displays were beyond anything I've encountered. The only suitable name for him was Kandinsky. Kandinsky had fixed habits and a definite home. Unlike Matisse, he did not have a single notable colour. He produced the same kinds of patterns and colours that the others did, but in a more extravagant way. For about a week in 2009, when I was trying to get the perfect photograph of him, I would visit him in his home. I'd arrive in the late afternoon each day and wait at the surface above his den, which was about 12 feet down. He would eventually emerge and come up to man the top of his rock, facing out to the ocean side. He held 2 arms aloft, with the others roaming about below them. I would swim down to meet him. When I arrived, he would have arms going everywhere, like a collection of ceremonial lances. Sometimes he would knot a couple of arms together over his head. Raised arms are often a sign of agitation, sometimes hostility, but I don't think this was true of Kandinsky, as he tended to produce such elaborate shapes continually, even when I was a fair distance away. On his skin, Kandinsky favoured flaring mixtures of red and orange, including a kind of pale orange-green, and he often combined these colours with the passing cloud display, on which waves of dark shapes flow over the skin. Tear-like patterns moved down a pair of his inner arms. After hovering in the water near his favourite rock for a while, he would set off to tour the shallows. He was not one of the friendly cuttlefish, but he would allow me to follow closely as he roamed in loops through the reefs around his den. While some cuttlefish seem friendly and curious, a second style of response to an exploring diver is intense hostility. Fortunately, this is rarer than friendliness. The most spectacular case I remember was an encounter with a large male cuttlefish in a spot where some very friendly ones have lived. Whenever I turn up at that rocky ledge, I'm reminded of those amiable meetings. This time I found a perfect expression of animosity, choreographed in colour and shape. I arrived and saw first a swirl of arms under the rock ledge. The arms were yellow-orange-brown. The animal was facing out, surrounded by waving seaweed, with arms going everywhere. I thought initially this behaviour might be camouflage, that his waving was matched to the seaweed. I came closer and found him producing more colours, silver-white welts. These were not the relaxed pulsations of silver around the face and arms that are common, but larger blotches that would flare on and off. His lower arms were fanned out below, and the other arms were a forest of horns. He was instantly watchful, and very soon he was coming out at me fast. I swam backward in a hurry. He kept coming for some distance and then left the chase and returned to the den. I waited and then approached cautiously again. Out he came like a jet-propelled medieval siege device. On these chases he produced the most murderous-looking displays I've ever seen. Burning orange colours, arms like horns and sickles, and skin folds resembling bent iron armour. Sometimes his inner arms were held high, contorted. At one point he held nearly all his arms aloft and twisted together, with just one set of arms below and his face between. I thought, he looks like the jaws of hell. It was as if he, in his molluscan way, had a real sense of what is frightening for a human and was trying to produce a vision of damnation, something intended to strike at our hearts. I persisted with him and kept cautiously returning. He continued to chase me off, but I soon noticed that these charges never quite reached me. And this remained so when I began to retreat more slowly. I wondered how much bluff there was in his advances and how much genuine violent intent. Eventually I tried a new tack. If he is waving his arms murderously at me, why not wave back? The next time he came out, I retreated much less and lifted my arms in front of me with scuba gear going everywhere. That got his attention. He still made as if to come forward, but did not actually move much, and the flailing arms began to calm down. He reduced his displays more and more, and soon his arms were at rest, and the spiky skin folds receded. I was finally able to come close to him. He stopped facing straight at me and seemed to be looking at an angle, off over my shoulder, much more relaxed. Once I moved directly in front of him, and he suddenly came at me again, his head lowered at first and then roiling with arms. I decided that we'd become as friendly as we were going to get. There is another notable mode of human-cuttlefish interaction, though interaction's not quite the right word. Some cuttlefish behave with a level of indifference that is so intense it is hard to describe. In some ways, this is the most intriguing behaviour. These cuttlefish do not seem to register you as a living being at all. When they're still, they tend not to face a person directly, as others quite often do, but look off past one's shoulder. If you move a little, they adjust too. There's a maintenance of the non-contact. This profound indifference is seen in some cuttlefish as they go on looping excursions around their reefs. On these trips, a cuttlefish might poke around under rocks or just wander about. Much of the time they're probably looking for food or mates, but they often do not seem to be looking very hard. Touring cuttlefish can sometimes be friendly, or at least curious, stopping to peer at you before swimming on, but some are able to ignore you no matter how close you swim, even if you're right alongside their eye. Once I was being ignored so perfectly that I planted myself directly in the animal's path just to see what he would do. What followed felt like an existentialist game of chicken. He came closer and closer, refusing to acknowledge my presence until he was just a foot or so away. Then he looked up at me with an expression that I cannot describe at all, except to say that he seemed deeply unimpressed, edged past, and swam on. What role do we have, then? What are we to them? Surely we are registered as large, mobile creatures. Surely then we might be potentially dangerous, or at least something of interest. Other cuttlefish do see us that way, as visitors to study or to chase off with a wild display. But sometimes it appears that we do not come across as living beings at all. Being ignored so deeply makes you wonder if you're entirely real in their watery world, as if you're one of those ghosts who does not realize they are a ghost. Seeing colours. With our picture of cephalopod colours nearly complete, we now reach a fact that makes absolutely no sense. Cephalopods, in almost all cases, are said to be colourblind. This impossible conclusion is based on both physiological and behavioural evidence. First, any system for detecting colour differences requires something in the eye that can distinguish differences in the brightness of light from differences in its colour. The usual way this is done is to have several kinds of photoreceptors. Photoreceptor cells contain molecules that change their shape when they are hit by light. The change in shape triggers other chemical events in the cell. Photoreceptors are the interface between the world of light and the signaling network of the brain. Any eye must contain something like this. For colour vision, you need to have a range of photoreceptors that respond differently to the different wavelengths of the light that comes in. Most humans have 3 kinds of photoreceptors. Colour vision, using this system, requires at least 2. Most cephalopods have only 1. Behavioural tests have also been done on some species. Can a cephalopod learn to make a distinction between 2 stimuli that differ only in colour and in no other way? Apparently the ones that have been tested cannot. This is baffling. These animals are doing so much with colour. They're also superb at matching the colour of their surroundings for camouflage. How can you match colours you cannot see? Biologists sometimes offer explanations along these lines. First, cephalopods may be using subtle differences in brightness as indicators of the likely colours, hues of objects around them, given the typical colours in their environment. Second, the reflecting cells, the mirrors in the skin, can help. You can produce a colour you cannot see by reflecting it back from outside. This makes sense of some of what cephalopods can do. Camouflage can be achieved with reflection, if the colour you aim to match in your background is also coming toward you from other directions. Simple reflection cannot be the explanation if an animal is matching a colour behind its back, while the light coming in from the front is different. In that case, the cephalopod would have to actively produce the right colour through some combination of chromatophores and reflecting cells, and it would have to know which colour to produce. Cephalopods do seem to be able to do this. They often seem to match a colour that is behind them when different colours are in front. During the period I was writing this book, some pieces of this puzzle began to fall into place. The first pieces were put down in 2010 when Lydia Methger, Stephen Roberts and Roger Hanlon published a paper reporting that the photoreceptor molecules in the eyes of one kind of cuttlefish are probably also present in the cuttlefish's skin. That alone does not show much for several reasons. First, it's possible that these molecules do something unrelated to seeing when they're found outside the eyes. Second, even if the light-sensitive molecules in the skin were indeed responding to light, this would not solve the colour vision problem. There is still just one kind of photoreceptor molecule in the animal, even if it appears in strange places. You can't see colour, it's thought, with only one photoreceptor. For some years after the Methger-Roberts-Hanlon result was published, there was little follow-up. Through the internet, I found just one person who seemed to be working on it, Desmond Ramirez, a graduate student in California. When I reached him, he confirmed that he was working on the problem, but played his cards close to his chest. Another couple of years passed. I'd just sent off a book review in which I wondered why the old lead was not being followed, and just days later Ramirez published his paper. The paper, written with Todd Oakley, showed first that photoreceptor genes are active in the skin of a particular octopus species, Octopus bimaculoides. Crucially, it also showed that the skin of this octopus is sensitive to light and can change the shape of the chromatophores even when the skin is detached from the body. Octopus skin itself can both sense light and also produce a response that affects the skin's colour. Back in Chapter 3, I discussed the way that an octopus's nervous system is spread throughout much of its body. The image I tried to develop in that chapter was one of a body that is its own controller to some extent, rather than a body steered around by the brain. Now we learn that an octopus can see with its skin. The skin is not only affected by light, something true of quite a few animals, but it responds by changing its own delicate pixel-like colour-controlling machinery. What could it be like to see with your skin? There could be no focusing of an image. Only general changes and washes of light could be detected. We don't yet know whether the skin's sensing is communicated to the brain or whether the information remains local. Both possibilities stretch the imagination. If the skin's sensing is carried to the brain, then the animal's visual sensitivity would extend in all directions, beyond where the eyes can reach. If the skin's sensing does not reach the brain, then each arm might see for itself and keep what it sees to itself. The Ramirez and Oakley finding is an important development, but it does not yet solve the problem I emphasized before, the problem of color perception. The photoreceptor in the skin of Ramirez and Oakley's octopuses is sensitive to the same wavelengths as the photoreceptor in the eye. Even if the whole body can see, it seems that it must be seeing in monochrome. The problem of color match remains. I suspect, though, that the Ramirez work will lead to a resolution of this problem. A hint was offered in the older paper by Methke and her colleagues. They noted that even if the photoreceptors in the skin are chemically the same as the ones in the eye, their light sensing might be modulated by the chromatophores or other cells around them. This might permit one kind of photoreceptor to behave like two. Some butterflies use a similar trick. This could work in several ways. One possibility is that a chromatophore might sit on top of a light-sensitive cell acting like a filter. That photoreceptor would then respond to coloured light differently from a photoreceptor paired with a differently coloured chromatophore. Another possibility was suggested to me by Lou Jost, an ecologist, orchid expert and artist. He suggested that the act of changing colours might do the trick. Suppose some light-sensitive cells sit below a layer of many chromatophores. As chromatophores of different colours expanded and contracted, the light passing through them would be affected in different ways. If the animal kept track of which chromatophores were expanded, as well as how much light was reaching its sensors, it could know something about the colour of incoming light. The animal would be like a cameraman exchanging one filter for another as it went through its colour changes. A monochrome sensor can detect colour if the organism has filters of different colours and knows which ones are operating at each moment. All these possibilities depend on the location of the light-sensitive cells in relation to chromatophores, and on other unknowns. But in some ways it would be surprising if one of these mechanisms was not operating. As long as some light-sensitive structures lie below the coloured chromatophores, when the animal performs its chromatophore changes, there will inevitably be effects on the light-sensitive structures below, and these effects will correlate with the colour of incoming light. The information is available. It would not seem to be a difficult evolutionary transition for the animal to put this information to use. Being seen. When it comes to camouflage, octopuses are unsurpassed. They can be completely invisible to an observer looking for octopuses just a few feet away. They are helped by the fact that, unlike cuttlefish, octopuses have almost no hard parts in their bodies and can assume just about any shape at all. Giant cuttlefish cannot fool observers as completely as octopuses can, but some cuttlefish come close. The best act of cuttlefish camouflage I have seen was the work of a reaper cuttlefish. This is a smaller species, growing to about 6 inches long. The grim name is quite misleading, as these are the sweetest-looking animals imaginable. They're usually a soft red with yellow eyeliner. I found this one on some seaweed. Once we saw each other, he was very wary. He evaded me, swimming through weeds and around rocks, keeping obstacles between us. At one point, he disappeared into a flat channel with a few rocks strewn around. In a moment, I could not see him. I knew that these cuttlefish can take on a mottled rock-like appearance, so I was positively expecting to find him somewhere, trying to be a rock. There was a small rock in the middle of the channel. I looked and thought, well, that one is just a rock. I went to the other end of the channel where he should have come out, and there was no sign of him. I came back around to look at the channel again, and at the rock. Looking closer, it was the cuttlefish. Once it was apparent that I was fixated on him, he gave up the rock camouflage and wandered back into his dark pink. So there I was, looking for a small cuttlefish looking like a rock in that exact spot, but he fooled me anyway. Suddenly then, as I watched him change colours, a grey moray eel raced out with jaws open and attacked him. There was a burst of ink from the cuttlefish. They have ink of the same sort as octopuses and squid. It looked like a cloud of black smoke, as if he'd caught fire. I tried to see into the channel, which was now black, and caught only a brief glimpse of the cuttlefish being helplessly shaken and swept about by the eel. I felt terrible, as it seemed likely that I'd distracted the cuttlefish and allowed the eel his chance. Ink continued to billow out. Given the violence of the eel's attack, I'd soon given up on the cuttlefish, but then he zoomed up out of the black cloud, wildly coloured and strangely flattened, with his fins fanned out. He looked dazed, damaged, but still able to swim. He had just one large bite mark on the back of his body and was still wearing his yellow eyeliner. At first he swam in a chaotic, punch-drunk meander. Then he straightened up and headed down toward another ledge. I was amazed to see him. I think of a moray eel as a consummate predator, especially in that close-range context among rocks and weeds. They're all teeth, muscles, and snake-like strength. Once the eel was on him, it seemed there was no contest. The cuttlefish had no teeth or bones or armour. Rather than a flattened serpent, it looked like a toy hovercraft. Yet the cuttlefish escaped. The original function of cephalopods colour change, the reason it evolved, is thought to be camouflage. As cephalopods gave up their shells and began prowling waters full of sharp-toothed fish, camouflage was one way they avoided being eaten. Camouflage is the opposite of signalling. It's producing colours in order not to be seen or recognised. In some species, signalling then arose. The camouflage machinery was pressed into service as a way of communicating and broadcasting. Colours and patterns were now produced to be seen and noted by observers, such as rivals or potential mates. Intermediate between the clear cases of camouflage and of signalling are diamatic displays. These are dramatic patterns often produced while fleeing a predator. It's hypothesized that they're an attempt to startle or confuse the foe, to suddenly look different and weird in a way that might lead the predator to pause or lose their bearings. Here the display is supposed to be noticed, but it does not send information to a receiver. It is merely supposed to be confusing or disruptive. During their mating period, giant cuttlefish males engage in ritualized displays that include an elaborate mix of skin displays and body contortions. This is seen most dramatically in one place on the southern coast of Australia, near an industrial town called Whyalla. Here, thousands of giant cuttlefish gather off the coast each winter to mate and lay eggs in shallow water. No one knows why they choose this particular spot, but it's a great place to watch the most dramatic of all cephalopod signalling. A large male will try to act as a consort to a female, monopolizing her and keeping other males away. When a rival male approaches, the consort and the intruder begin competitive displays. The two males will lie side by side quite close in the water. Each will stretch out as far as it can, often with a gentle curve in its body. They will blaze with colour changes and patterns. Having stretched one way, a cuttlefish will often turn 180 degrees around and stretch out in the other direction. This turning, unfussed and deliberate, looks like a dance from the court of some civilized French king. The stretching, in contrast, looks like competitive yoga. The mix of yoga and courtly dance suffices to determine which cuttlefish is larger, and the larger almost always prevails. The smaller one will back off. The female will drift quietly in the water, perhaps staying close to her pulsating companion, perhaps wandering away. Cuttlefish sex, if it results, is a peaceful affair by the standards of the animal kingdom. They mate head to head. The male attempts to grasp the female front on. If she accepts him, he will envelop the female's head with his arms. Having reached this position, there are a couple of minutes of stillness. Apparently he's blowing water at her with his funnel during this period. The male then uses his left fourth arm to take a sperm packet and place it in a special receptacle below the female's beak, and with more rapid motions, he breaks the packet open. They separate. Squid also engage in a considerable amount of signalling, much of it complicated and puzzling in its role. Some signals are clear and common to several species. When a male approaches a female, she will sometimes display a definite white stripe that says, "No thanks." In a moment I'll say more about some of these signalling systems, but first I want to outline something else I've come to believe about cuttlefish colours. Let's accept that camouflage and signalling are the two functions of colour change in cephalopods. It's due to them that colour change evolved and is maintained. The fact that those are the functions of colour change does not mean that every colour you see is produced as a signal or as camouflage. I think that some cephalopods, especially cuttlefish, have an expressiveness that goes beyond anything with a biological function. Many patterns seem to be anything but camouflage, and are also produced when no obvious receiver of the signal is around. Some cuttlefish and a few octopuses go through an almost continual, kaleidoscopic process of colour change that appears disconnected from anything going on outside them, and appears instead to be an inadvertent expression of the electrochemical tumult inside them. Once the colour-making machinery on the skin is wired to the electrical network of the brain, all sorts of colours and patterns might be produced that are simply side effects of what is going on within. That is how I interpret the colours of many giant cuttlefish. They're an inadvertent expression of the animal's inner processes. Such patterns include flares and surges of activity and also subtler changes. If you look closely at the face of a giant cuttlefish, the area between its eyes and down the first part of its arms, you'll often see an ongoing murmur of very small colour changes. Perhaps the machinery of colour change is in an idling state there. I spent several days visiting a cuttlefish I called Brancusi. He rarely produced bright colours. Instead, he would sometimes fix a few of his arms into an unusual pattern and then hold the shape completely still, like a sculpture, for as long as I was able to stay with him. He would hold up a pair of inside arms like horns, but angle the top of them down toward the seafloor. Brancusi favoured shape rather than colour, but if I looked closely I would see a constant restlessness in all the colours on his face. In other animals I've often seen steady pulsing changes just beneath the eyes, like animated eyeshadow. I accept that cuttlefish can control their skin closely when they want to. They can snap into camouflage or an aggressive display very quickly. Any colour changes that do not contribute to signalling and camouflage as side effects, from an evolutionary point of view. If they did much harm, they would probably be suppressed. But perhaps they do not do much harm. More precisely, perhaps they would do harm, attracting unwanted attention in smaller cephalopods, but do not do much harm in a giant cuttlefish, an animal big enough for many predators to pass by. Another possibility is connected to the speculative ideas about colour sensing I described earlier. Suppose that by changing its colours, a cephalopod affects the light that reaches sensors within its skin. Then some of these ongoing low-level colour changes might be a way of surveying the chromatic environment. I realise also that a lot of the colour changes that puzzle me might be triggered by my own presence. I often try to keep some distance away and off to the side when watching these displays. I've also set up video cameras at octopus dens and then left for a few hours to see what they do when no one is around. The animals often go through unexplained sequences of colours even when, as far as I can tell, no other octopuses are nearby. Perhaps the camera is their intended audience in these cases. That's possible. But another possibility is one that takes things more at face value. I think these animals have a sophisticated system designed for camouflage and signalling, but one that is connected to the brain in a way that leads to all sorts of strange expressive quirks, to a kind of ongoing chromatic chatter. Baboon and squid. Signals are sent and received. They're made to be seen or heard. To look more closely at sender-receiver relationships in animals, we'll emerge from the water and switch to a very different case. Wild baboons in the Okavango Delta of Botswana, Africa, have been studied for years by Dorothy Cheney and Robert Seyfarth, two of the most influential researchers into animal behaviour. The life of a baboon is a fraught one. There are constant risks from the great African predators and also an intense shifting social scene to contend with. Baboons live in troops. The one Cheney and Seyfarth studied contained about 80 individuals with a complicated dominance hierarchy. Female baboons remain in the troop they were born into and form a hierarchy of families, matrilines, with further dominance relations within each matriline. Most males leave the group of their birth and migrate into another as young adults. They live shorter and tougher lives, with more violence and many exhausting chases and displays. They're frequently driven off or drive others off. Even when the composition of a group is stable, both sexes face challenges and shifts, form alliances and friendships, and do a lot of grooming. All this is meticulously documented by Cheney and Seyfarth in the book Baboon Metaphysics. Given the complex social life, it's not surprising that there is communication. But baboons can make only fairly simple sounds, calls of 3 or 4 kinds, especially threats, friendship grunts, and submissive screams. Communication itself is simple, but as Cheney and Seyfarth show, it gives rise to some sophisticated behaviours. Each individual calls in a distinctive way, and a baboon can recognise who has just called. They know who has threatened and who has backed off. Cheney, Seyfarth, and others worked out by means of ingenious playback experiments that a baboon hearing a series of calls is able to process it in very rich ways. Suppose a baboon hears this sequence coming from a location it can't see. A threatens and B backs down. What does this mean? It depends who A and B are. If A is higher in the hierarchy than B, it's not surprising or notable. But if A is below B, then a sequence in which A threatens and B backs down is surprising and important. It indicates a change in the hierarchy, something that will matter to a great many members of the troop. In the playback experiments, a baboon would behave differently, being much more attentive when a series of calls indicated an important event of this kind. As Cheney and Seyfarth say, it seems that the baboons construct a narrative from the series of sounds they hear. This is a tool they use for the purposes of social navigation. Compare the baboons with the cephalopods. In baboons, the production side of their vocal communication system is very simple. There are only 3 or 4 calls. An individual's choices are limited, and a call will reliably follow interactions of a particular kind. The interpretation side, though, is complex, because calls are produced in ways that allow a narrative to be put together. The baboons have simple production, complex interpretation. The cephalopods are the opposite. The production side is vastly, almost indefinitely complex, with millions of pixels on the skin and a huge number of patterns that might be produced at each moment. As a communication channel, the bandwidth of this system is extraordinary. You could say anything with it, if you had a way to encode the messages and if anyone was listening. In cephalopods, though, social life is much less complicated than it is in baboons, as far as anyone can tell. I will discuss some surprises later and in the last chapter, but they won't change this comparison. No one thinks any cephalopod has a social life comparable to that of a baboon. Here we have a very powerful signal production system, but most of what is said is going unnoticed. Perhaps that's not the right way to put it. Perhaps because no one is interpreting most of it, little is really being said. But it's also true that with all the chatter, all the mumbling of the skin, a lot of what is going on inside is made available on the outside. Signal production in one cephalopod species, the Caribbean reef squid, was documented extensively back in the 1970s and 1980s by two researchers working in Panama, Martin Moynihan and Arcadio Rodoniche. They followed their animals in the field for years, recording their behaviors in detail. They found a lot of complexity in the patterns being produced, so much so that they suggested the squid have a visual language with a grammar, with nouns and adjectives and so on. This was quite a radical claim to make. They published their ideas in a monograph that appeared in a very respectable journal, but it was an unusual publication, with personal reflections and ongoing attempts to get inside the world of these skittish animals, whom they patiently followed around all day with snorkels. The monograph was also beautifully illustrated by Rodoniche, who later retired from science and became an artist. The argument for a visual language was made by showing the complexity of squid displays. These displays combined colours and body postures. Some of them are tiny analogues of giant cuttlefish displays described previously. Moynihan and Rodoniche charted the sequences they saw: golden eyebrows, dark arms, downward pointing, flecked yellow, upward curl. I once chased one of these squid over a reef in Belize, and was struck as they were by the complexity of what it was doing. But there is a mismatch in Moynihan and Rodoniche's own discussion, one that they were aware of, but perhaps did not fully confront. Communication is a matter of sending and receiving, speaking and hearing, producing and interpreting, two complementary roles. Moynihan and Rodoniche were able to document a lot of very complicated production of signs, but they said much less about the signs' effects, how the patterns were being interpreted. They were able to work out a few fairly clear sign and response combinations in mating situations, but many of the displays they observed were produced outside that context. In total, they counted about 30 ritualized displays and many patterns in the sequences and combinations of displays that were produced. They said that these patterns must have some meaning, but in most cases they could not work out what it was. We cannot ourselves, in the present state of our knowledge, always and in every case, tell the difference in message or meaning between every observed arrangement of particular patterns. We feel, nevertheless, that we must assume that there is a real, functional difference of some sort between any two sequences or combinations that can be distinguished from one another. By their own lights, there was not a lot of complexity in the behavioral interactions between one squid and another. Why, then, were such complex displays being produced? There's a genuine puzzle here. Even if Moynihan and Rodoniche were overcounting the signals and making too much of the analogy with language, there's still a question about why the squid seemed to be saying so much. It's possible that the sequences of colours, poses and displays played various subtle social roles. Later researchers have been a bit sceptical about this part of Moynihan and Rodoniche's work. But perhaps there's more going on than we can tell. These squid are among the most social of cephalopods. The contrast between the baboons and the cephalopods is, I hope, vivid. In the cephalopods we find, as a result of their heritage of camouflage, an immensely rich expressive capacity. A video screen is tied directly to their brain. Cuttlefish and other cephalopods are brimming with output, publish or perish. To some extent, this output is designed by evolution to be seen. Sometimes it is camouflage, but sometimes it is meant to be noticed by rivals and the opposite sex. the screen also seems to run through much chatter and murmuring, happenstance expression. And even if cephalopods have hidden powers of colour perception, a lot of their wild chromatic output is surely lost on watchers. The baboons, on the other hand, can say hardly anything. Their channel of communication is very limited, but they hear much more. These are both partial cases, unfinished, in a sense. Though one should not think of evolution as goal-directed, evolution is not heading anywhere, not toward us or anyone else. But I can't resist seeing in both animals an unfinished quality. They're both animals with a one-sidedness in their version of the fundamental signalling duality, the interlocking roles of sender and receiver, producer and interpreter. On the baboon side, there's a soap opera life, frantic and stressful social complexity, and little means to express it. On the cephalopod side, there's a simpler social life, hence less to say, but such extraordinary things expressed nonetheless. Symphony. Late one summer afternoon, I swam down on scuba to a favoured place, a den where I've seen many giant cuttlefish. A cuttlefish was there. He was medium-sized, probably male, and even from some distance I could see that he had intense colours. He did not mind my arrival, but was not curious or watchful. He was very still. I set myself up next to him, just outside his den. As he faced out past me toward the sea, I watched as his colours changed. The series was mesmerising. I noted right away a rust colour, different from the reds and oranges one usually sees. You would think that every shade of red and orange had been covered 100 times by animals I'd seen. But this one seemed unusual, a rust with brick. There were also grey-greens, other reds and faint pale colours I could not quite catch. As I watched, I realised that these colours were changing in a concerted way, and changing in more ways than I could track. It reminded me of music, of chords changing amid and over each other. He would shift several colours in sequence or together, I was not noticing which, and end up with a new pattern, a new combination which might stay still for a time or immediately start shifting into another. There were dark yellow, pale brown combinations, red combinations that were more familiar, and others. What was he doing? It was slowly getting darker in the water, and under his ledge it was already quite dark. He was not displaying much with his body. I remained off to the side as still as I could be and breathing as little as possible. The eye facing me seemed nearly closed, but I've learned that cuttlefish are able to see more than one might expect, with their eyes mostly shut. He looked out into the darkening sea where yellow-green seaweed was waving. Given this motion, I wondered whether this might be a case of the passive production of colours, reflecting the mix coming in. But the movement through colours seemed more organised than that. Many of the colours had no analogues outside. He kept moving through his chords. I crouched low among the weeds. It occurred to me that he was paying so little attention to me that all of this might have been going on while he was asleep or half asleep in a state of deep rest. Perhaps the part of his brain that controls the skin was turning over a sequence of colours of its own accord. I wondered if this was a cuttlefish dream. I was reminded of dogs dreaming, their paws moving while they make tiny yip-like sounds. He made almost no movement except small adjustments of siphon and fin that kept him hovering in the same place. He seemed to be maintaining as little physical activity as possible, except for the ceaseless turnover of colours and patterns on his skin. Then things started to change. He seemed to stiffen or pull together and began going through a long series of displays. It was the strangest series I have seen, especially as it seemed to have no target or object. During almost all of the sequence, he faced well away from me out to sea. He pulled in his arms and exposed his beak. He tucked his arms below him in a missile-like pose, then produced a yellow flare. I kept glancing out to see if he was looking at someone, another cuttlefish or some other intruder. There was never anyone there. At one point he went into the sideways stretch that males do when they're competing with each other. Then he pulled himself into the most extraordinarily contorted shape, his skin suddenly white, with arms pulled back both above and below his head. This sequence then quieted down. I backed off and moved higher in the water, remaining beside the den and not in front of it, and watching him calm down. And then instantly he seized into a wild, aggressive pose, with arms straight out, sharp like thin swords, and his whole body a bright yellow-orange. It was as if the orchestra suddenly hit a wild, clashing chord. The arms ended in needles, his body became covered with jagged papillae like armour. He then began roaming a little, sometimes facing me and sometimes facing out to sea. I wondered again if this was all directed at me, but if it was a display, it seemed to be aimed in directions all around, and I'd been back from the den when this sequence started, when he exploded into yellow-orange and the needle-arm pose. Still facing away, he began to ease back from this fortissimo. Though he moved through a few more permutations and poses, they were subsiding. And then he was still, his arms hanging down, his skin a quietly shifting mixture of the reds, rusts, and greens that he'd been producing when I arrived. Turning, he looked at me. I was now cold, and the water was getting steadily darker. I'd been there beside him for perhaps 40 minutes. Now he was calm, and with the symphony or dream over, I swam in.